So for your when is your exam? 28, right? Okay, so for your exam, so there is some reading material. No, not reading material. There are some things that you can do to prepare. So midterm review. Okay. We will not do it today, but someday. So midterm review, what you can do, we have discussed all this, chapters 1, 2, 3 and 4. We have discussed some more also, so I'll post them later. So what you can do is for this, there are some practice problems. Most of these practice problems are from the book. So go to the book, look at the practice problems and just do them. Right? And I will discuss some practice problems. So these are numerical problems. These are everything that we are discussing in class that we have slides for. Right? So numerical problems will be only from the content for which we have slides. Now there are some concepts that we are discussing for which we don't have slides. Right? And we don't have them in the book. We have to read papers. So for those I will publish and not publish. I will upload papers, but I won't ask numericals from them. Mostly they will be conceptual questions. So if you go, there are a lot of things, a lot of examples here. Go to the book, and you can also go to this exam. If you go to the exams folder, I have midterm solutions. So this is the last year's midterm. You can practice that as well, although it won't be there. Right? You will not have these same questions. But these are the types of those questions. So yeah, look at these. So this will be the structure of your exam also. You have 5 questions, each 10 points, each some points, and then you'll have some extra credit. So yeah, try to prepare for that. And I will do a midterm review maybe on, when is it? 28, right? So I can do it maybe on 21st. We will do midterm review on 21st. So do you have any questions or any questions on the material we have discussed so far? Do you want something more, something less? Yes.
You have skipped a few topics like box plot, static plot. You ask
Where? Which?
like you haven't discussed any numericals on that. So you ask
Numericals on what? Box?
some chapter 3 box.
For chapter 3, yeah, those are just so those are data visualization techniques. We haven't gone in depth to those. So I won't ask questions. Whichever I didn't go in depth, we won't ask questions. Any other things that you want to discuss? Okay, so let's continue our discussion. So we are trying to go towards deep learning. And we failed last time. Let's see if we succeed this time. So we are discussing restricted Boltzmann method. Let's start from here. Now we before that we have discussed belief networks. Right? And belief networks, we said that they are good tools to express conditional independence in the general case. Because we said Naive-Bayes classifies a specific type of belief network. Right? So it also expresses conditional independence, but it has a big assumption that given the class, all the attributes are conditionally independent of each other. Right? So that is a big assumption. But belief networks doesn't make any such assumption. So whatever conditional independence you select, you choose, you understand, you can express using belief networks. The problem with belief networks is in general it is very difficult to learn the belief network. Because there are two components of learning. First is, you know the nodes, that's not a big problem, but what are the edges? Edges means which elements are conditionally independent of the other. So this is still an issue of research and there is no correct answer. Much like a decision tree. Right? Decision tree goes by impurity matrix. Now, which impurity matrix is good, you don't know. It's just a greedy algorithm. And even if is greedy algorithm good, you don't know. Nobody knows. So same as same with belief networks. So there are many different works which use certain metrics to figure out conditional independence. One work I showed you. These are all research papers. So one work that tries to do mutual information, and there is a big formula giving you mutual information. So that those are different types of works that you can look into. But yes, it's difficult to learn belief networks. So it can get messy because you can get as many nodes, different types of connections. Instead of getting a nice feed-forward network, you can get a mesh. Right? So it becomes very messy. So to simplify the learning method, to simplify the learning procedure, you have a restricted Boltzmann machine. Right? Restricted Boltzmann machine is a directed acyclic graph, and it is a bipartite graph. Bipartite graph means that there are only two sets of nodes. Right? So this is the visible node. It is called visible layer, and there is a hidden layer. Right? There is a hidden layer. So these are two sets of nodes in a graph, and it's a complete bipartite graph, which means every visible node is connected to all the hidden nodes, and all hidden nodes are connected to all visible nodes. But what is the difference between this and just a complete graph? Visible nodes are not connected to each other, hidden nodes are not connected to each other. Right? So that's why it's a bipartite graph. Now the thing is, there is a common misconception with the term visible layer and hidden layer. Now this question was just asked by one of the students, that okay, this is hidden layer, how can I use the output of this layer? So the answer to that is that this hidden layer, yes, the name is hidden, but you can see it. It is not like you can never see this layer. You can see it, you can get access to the output. The term hidden does not mean that the output just vanishes. Right? So you get access to the output. Now what you do with it, that's how the name hidden came into place. So the output of this is not an output that you make inferences with. So you don't say that, okay, this hidden layer output is 1, then that means this should be the recommendation. You don't make those arguments. You make those arguments only on visible layer. So visible layer is the layer that is interesting to common people. Hidden layer is not interesting to common people. So in the case of movie recommendations that we are doing, whether a movie is sci-fi, comedy, or whether a person likes sci-fi, comedy, or action, doesn't matter to that person. The person just wants to see some movies. But whether this is sci-fi, comedy, or action matters to the person who is recommending movies. So, but it doesn't matter to the end user. So that's why you can call it a hidden layer, because the layer, the results of the layer does not matter to the end user. But this does not mean that you can never see the output. You can use the output, you can see the output, you can use the output, and you can do whatever with it. So that is one of the concepts that we need to understand. Same with a deep feed-forward network. Deep feed-forward network means, you know, feed-forward network. We have seen ANNs and multiple just neurons connected to each other. It can be a bipartite, it can be non-bipartite, doesn't matter. Just neurons, one layer of neurons connected to the forward layer, then that layer is connected to another forward layer, and so on. So what is a deep ANN? Just have more layers. It's very basic. It's not a very big thing. So now let's come back. Let's come back to the restricted Boltzmann machine, and let's see why is it useful. And why is there so much buzz about RBMs? No, there is not so much buzz about RBMs, but there is a lot of buzz about the things that RBM can help us. And so we'll talk about that. Because people don't know RBMs, but people know recommendation systems. Okay? So we are talking about, okay, there are 6 movies. We selected 6 movies, and we said that these movies have maybe 3 categories. And let's say there are 10 users, and each user has a recommendation for these movies, or has a rating. And these ratings are not just from 1 to 5, these ratings are whether like or don't like. Only these movies. So like is 1, don't like is 0. So whatever input you have here is either 1 or 0. So if you have 6 movies, there are 6 nodes in the visible layer. And if you have 4 categories, then there are 4 nodes in the hidden layer. Now this node belongs to movie 1. This node belongs to movie 2. This is 3, and so on. This is 6. And this belongs to the category 1, category 2, category 3, and category 4. Right? This notion of hidden layers you have given. So it's because you want to understand what the person likes. But it doesn't matter to the person. So now what you do? So these are all bipartite connections are all there. So what is the forward pass of this network? How do you do a forward pass on this network? So let's understand. So a forward pass, so if we represent it in terms of mathematics, then let's say xi belongs to the set of movies, and xj belongs to the set of categories. Let's have instead of xj, let's make it y, right? So let's say y is the set of categories, not yj. Yj are the set of categories. So what is yj? Yj is just the activation of these hidden layers. And what is xj? Xj is the 1 or 0 values on these visible layers. So xj or xi, sorry, xi can be either 0 or 1, right? And there and I can be between 1 to 6. Right? Similarly, okay, now let's see what is yj. J can be between 1 to 4. Right? Now let's see what is yj. So what you do with yj is you have these weights, each edge has a weight, right? So if you do yj, then what you do is you multiply by the weight wij, so it is an edge between I and j. If it is an edge between I and j, you use that weight wij, and you multiply with xi. You summation overall I equals 1 to 6, you add a bias, right? And then you add a activation function to it. Now this is not yet yj. You use this to get yj, but it's not yet yj. So let's say this is pj. Some variable. It's not the output, but some variable related to the hidden layer j. Right? Not hidden layer, hidden node j. So what is this activation function? This activation function sigma with respect to x is some sort of a function that is like this. Some this kind of function. Yes, we have a question.
Are we assuming that we have already learned the weights in the...
No, there is no learning of weights right now. The weights are randomly assigned. Okay. For now, the weights are randomly assigned. Yes.
So for each user, there is a new argument because each user can have...
No. Just one argument.
Because it depends on the number of movies watched per user. So I can watch 10, the other person can watch 15 movies. So how do you...
No, let's say all users have watched these 6. Okay. There's just one argument. So this is an activation function, you have this, so the activation function is anything between 0 and 1. And if you have very high values of x, then it's almost 1. And if you have very low values of x, you have 0. Right? So now, what you do is, so this since sigma x is between 0 and 1, what you do is, you ensure that yj is equal to 1 with a probability pj and is equal to 0 with a probability 1 minus pj. So some Bernoulli sampling. Somebody was asking that why don't we just do majority? Just look at the majority who's what type of movies this person is watching, and then just say that okay, this person likes watching sci-fi. That person is not here maybe. So we'll come to that question, and that question lies in this arrangement. So there is a probability associated with it. So yj becomes 1 with a probability of pj, and it becomes 0 with the probability of 1 minus pj. Okay. So that is the forward pass. Yes.
Where does the rating come into picture?
Rating?
The user has given like or
Ones and zeros, xi. These are the ratings.
so if xi is 0, then it will just consider the bias, that's it.
No, it's summation. So if all are 0, then yes, bias. No, you don't like anything. But if there is a system where all users don't like any movie, then there is no recommendation. Right? Everything is disliked by everyone. So there will be some ones in the exchange that is acceptable to assume. So you make yj equals 1 with the probability of pj and yj equals 0 with the probability of 1 minus pj, right? So now, let's make an association. So, ideally, what we would want is that, let's say this is a sci-fi movie. Let's say this node is for sci-fi, and this movie 1 is a sci-fi movie. Right? Then if you have learned your RBM and your RBM is good, your ideal output should be that if you give 1, 0, 0, 0, 0, 0, then your sci-fi movie should get triggered, right? Because this person likes sci-fi, right? So ideally, you should have an association with this and this. And if this is 0, you should not have this as 1, you should have this as 0. Right? That is what ideally it should be. So then what you do, that this metric xi multiplied by yj, this metric captures this fact, captures an association of movies with their types. So which means that if the RBM has successfully understood that the movie is a sci-fi movie, then it should have this hidden layer as 1 and this as 1 as well. Right? So in that case x1, y1 would be 1. So if x1, y1 is 1, then that means it encodes an association of the movies with their types. Okay. Now what is this number? What is this encoding? So what I am doing, I am taking one movie, multiplying it with all the YJs, right? all the categories, and then taking another movie, multiplying with all the categories, taking another movie, multiplying with all the categories, and summing them up. So ideally, if the RBM is the best RBM in the world, what should this value be? No, 6. Because all movies are classified as the same, and are correctly classified in their categories, right? So this is a potential metric to learn, right? So what the learning algorithm of our RBM does is this. So it's a very interesting algorithm. So what you do is, for a set of xi's, right? So the set of xi's means you have 1, 0, 1, 1, 0, 0, right? So you have this is one training data, one training instance. So you have 10 users. Ideally 10 is not enough. You have 100 users. 1,000 users. So, but let's say you have 10 users. So you have 10 such vectors. So you have 10 training instances. So initially you assume random weights, and you have assumed random weights. So you calculate this forward pass, and you have calculated the forward pass. So now what happens is, there is this randomness associated with it. Even if the activation is pretty high, there is a chance that you make it 0. Right? Yes, you make it 1 with probability Pj, so even if Pj is high, say 0.99, there is still 0.01 the chance that it will be 0. Right? So now what you do is, you do this forward pass and you calculate this value. Let's call it PC. Actually, this is positive consequence. Right? Now, you have some YJs, some YJ configuration. This is randomly obtained, but following the probability distribution. Right? So you have some YJ, so you have 1, 0, 0, 1, let's assume. Right? and may or may not correspond to your input. It may or may not correspond to your input. Now what you do, using the same weights, you calculate the inputs. You calculate the inputs of the visible layer. So how do you calculate? So x bar, so xi bar becomes wij yj, now sum over j, right? That's it. Right? So now this xi bar may not be equal to xi, may not, right? For a particular training instance, it may not be equal to xi. So if it is not equal to xi, again calculate these I equals 1 to 6, I equals 1 to 4, xi bar yj. No, this is j. This is, let's name it in C. This is called negative consequence. Now ideally what do you want? You want xi bar to be same as xi, right? So if you let the RBM, if you train the RBM so that PC minus NC is nearly 0, then you are done. Then RBM is the best RBM in the world, right? So now what you can do is using some gradient descent method. Using some gradient descent method, try to reduce this. So what is one gradient descent method that you can use? Remember NLP? Or not NLP, what did we say about that? No, perceptrons, right? Remember perceptron learning? So what you do is, you can just update the weights. Just update using this rule, and this is a learning parameter. This is a learning parameter. So what you do is you do this update for every training instance, each training instance 10 times. Go back, forth, 10 times. Right. Updating, each time updating the weights. So that is how RBMs are trained. Now what is the use? Now, do you have any questions? Yeah.
PC minus NC is a constant. Then every feature, like every weight Wij will be updated similarly.
Yes.
So
Yeah.
it's like every time we subtract the constant to all the
All the weights, yes. Now when you use a different training, then this will change. Another training instance will change this in a different way. Yeah.
How is Wij same in both the equations? Like,
Because it's the same age. It's the same age. You are just going forward and backward on the same age. Any other question? Yes.
This Wij for each weight, like we have to calculate separately.
Yes. For all the weights you calculate at the same time.
So this Wij will be weight for just one node.
No. This is all the weights of all the edges. So what you do is this all the weights for all the edges. You do it once for one training sample. Then you repeat the same thing for that same training sample maybe 10 times. So you go forward, backward, update, forward, backward, update, forward, backward, update 10 times. Then you take another training sample. Again do forward, backward, update, forward, backward, update 10 times. Again you do another training example. Do forward, backward, and you do it for all the training examples.
First you update Wij over here, and then we go and check our negative
No, so you first do positive consequence, then negative consequence, update weight. Now this is a new weight, new RBM. Do the same thing again.
The bias and sigma are constant.
What bias B?
B and sigma.
You can update sigma. Where is sigma? Oh, activation. No, sigma is constant. Yeah, sigma you don't change. You can update B also, and you can update B in the same manner. But you can do update B in the same manner, or you can choose a fixed B also. It depends upon the specific problem.
B and sigma are not there in the second equation for Excel.
No, sigma is always there. Whenever you go forward, you have to do activation.
And back for backward?
Oh yes, for backward. No, yeah, for backward you also have to use the sigma. I forgot that. You don't do probability there, but you do sigma. Where is it? So here, right? So you don't do probability here, but you do sigma. Yeah.
Like xi a vector like yj or it's a single value which is
6 is single value, 1 or 0. Yj is also 1 or 0.
There is a chance that you will never converge.
Yeah, there is definitely a chance that it will never convert. It's the same chance for any neural network. So there is no guarantee, right? There is no guarantee that it will learn correctly, but somehow it learns. Yes.
Why are we not taking that PC minus NC as an error and updating each weight as a differentiation of that error?
Well, this actually that is what and it is supposed to do. Right? That is what it is supposed to do. If you do the math, that is what it will come to.
I mean, like, why are we not taking, like, in back propagation, you have differentiation of total error with respect to individual weights, and then you back propagate.
Yeah, you can use back propagation also. This is one way. This is the perceptron way of updating. You can use back propagation. That is also fine. So how you update weights is up to you. This is one way of doing it. Yes.
What does negative consequence actually indicate?
That's what I'm coming to. We'll come. Okay, so no more questions, right? So let's answer his question. So he is saying that, okay, what is this PCNC? What does this mean? I go forward pass when I do, what does it mean? When I use the hidden layers and do backward pass, what does it mean? What it means is that the forward pass means that you have the visible layer. Right? And then you are getting the outputs of the hidden layer. So forward pass is the reality. In reality, what is the data? And forward pass is the reality. What is the backward pass? Given the hidden layer, you are getting the visible layers. Visible layer in the backward pass is like a wild guess. It's a wild guess by the machine. So have a configuration of hidden layer and find out the visible units. That is a wild guess. So the training of Boltzmann RBM is to match the wild guess and the reality. And that's what the RBM is trying to do. So that's why you make PC equals NC. So that is a fantasy that never gets achieved. Right? But you can go close to it. So wild guess is the backward pass and reality is the forward pass. Right? So now when you have learned this RBM, what you can do is basically what RBM is a belief net. Right? It is just a belief net. So if you use a specific type of belief net, it's much simpler belief net. So if you so these are the visible layers, and if you, so let's say you use this layer to generate the visible layer. So after you have learned, so you have a lot of training samples and you have learned the RBM and you got the weights. What do you do with the visible layer, or what do you do with the hidden layer? So the hidden layer configures itself to the probability distribution of the input layer, or the visible layer. So which means now you can use a configuration of hidden layer, the output that you get will be a sample from the same probability distribution as the input. Whatever training data you use, it's a sample from that distribution. So that is what RBMs give you. So if that is the case, then what you can do, what you are doing is that you can, if the visible layer is 10,000 data points, 10,000 data points in dimension, if the visible layer dimension is 10,000, so 10,000 nodes are there. And let's say the hidden layer is just 500 nodes, right? This is a dimensionality reduction technique. So by just using 500 items, you are estimating 10,000 items. So you can consider this as similar to PCA, principal component analysis. Right? Certain dimensional reduction technique, and turns out RBM is used for dimensional reduction as well. They are used for dimensional reduction. Now this is so what will you do? You will just use the hidden layer activation, just figure out an activation and just go back, and you can generate an X, and you say that okay, that X is one data point in that signal, in that input signal. So if I say that okay, I like sci-fi, I like I don't like comedy, I like action movies. With this, I can get a recommendation. A recommendation which has the same probability distribution as thousands of users that I have chosen. Now, if you have a weird sense of movies, then that might not work. So let's say there is bloody scenes and you find it funny, then it won't work. Yes.
So all RBM is doing is it is making its weight in such a way that the training set is always like it's a custom. It's making its weight in such a way that the training set will always accustoming itself to the training set weight, right?
That's what every machine does.
But if now here the assumption is that that training set is a sample of all the training sets you have.
That every machine does. And if you think of any machine, you give it a training set, it will configure itself towards that training set. Now it depends upon whether that training set has enough variance or not. So did we discuss generalization error? No, we did, right? We did discuss. So generalization error depends upon training set. If you are 100% accurate with the training set, that's not a good idea. And that is why it is not a good idea, because you can use training sets to modulate the behavior of a machine. Any other questions? Yes.
What if it's the other way around, like hidden layer has more number of nodes than the input layer?
Okay, so that is what I am interested in, and that is a very, I didn't want to go into that, but I can little later. I will go later in the class. You can do that, but it is basically trying to learn different structures of the signal. So that is feature extraction. You are trying to extract features. So you have heard about CNNs. Have you heard about CNNs? And convolutional neural network. Why are CNNs so popular? So one very widespread argument is that CNNs can automatically extract features from images. Right? That is why CNN is most popular. But is there any machine that can automatically extract features from time series data? Not image, not video, but time series data. Say accelerometer. I am moving my arm and there is accelerometer. I want to extract features automatically from this accelerometer. Can I do that? I cannot use CNN because CNN needs image. Why do CNNs need image? CNNs only work on image. Why? Very simple argument. Anybody with image processing background?
Because they read features in the images.
What?
They read features in the pixels
Yes, so what features?
Convex
What?
shapes.
So in order to extract features in images, what do you need? Filters, right? You need filters. What is filter? What does a filter do? Convolution. The basic operation is convolution. Any feature extraction technique on images is a convolution. But if I tell you, okay, figure out histogram of gradients. I am giving you an image, give me histogram of gradients. Can CNN extract that feature? Histogram of gradients? Cannot, because that's not a convolutional feature. Histogram of gradients is not a convolutional feature, so it cannot extract that feature. But turns out you don't need it. You have so many, even edge detection is just a convolution. Right? So you have so many good feature extraction algorithms that are just convolution. You just use a CNN, it will test all types of convolution. Right? It will test all types of convolution. But come back to signals, one-dimensional signals, which do not have any image. Right? If you come back to one-dimensional signals, what is a parallel to CNN? Right now there is none. Can I say that I can extract any type of feature I want from this signal using a CNN or some deep learning network? Very difficult to do. Can I do peak detection in a signal using CNN? Highly nonlinear operation. Right? So how can we do that? So one idea that he raised is maybe have an RBM that has a bigger hidden layer than input. And if it has larger number of neurons. So if it has a larger number of neurons, then what I can do is instead of learning this xi, yj summation, I can learn distances. Right? Instead of this, I can learn maybe a xi squared minus yi squared in each dimension. So what is this distance? This is Euclidean distance. Right? What if I learn cosine? X dot summation. Oh, actually, this is learning cosine distance. So what if I want to learn Manhattan distance? Right? So I can learn different distances. So can I use RBM as a distance encoder? Right? If I use RBM as a distance encoder, so that means, have you heard about dynamic time warping, DTW? DTW, you should learn about that. Well, let's keep it for another day. We might talk about that. Let's keep it for another day. DTW is a nonlinear distance metric. So what happens is that we can just give you a brief overview. So let's say there are two signals, right? There are two signals. This is one signal, right? And then there is another signal which is this. So see this pattern is embedded in this signal, but in a smaller scale. So this pattern is the same as this pattern. So if I take DTW distance of these two signals, it should give me lower values. It should say that this signal is similar to that. So that is a way that DTW distance metric gives you a method to encode that. So if one particular subsequence is embedded in another signal, you can extract that. This is a highly nonlinear algorithm. How? Because you have to align, you have to stretch, you have to squish and find out distances. Highly nonlinear algorithm. Turns out you can implement that in, you can train an RBM to learn that. Not an RBM, but an autoencoder. So what is an autoencoder? Let's come to that. So before we come to that, there is more to it. So there is this RBM. And let's come back to topic. There is this RBM. There is this notion of, so we know belief network, but then there is this notion of deep belief network. deep belief network is nothing but a stacked RBM. Stacked RBM is what? So you have a huge set of visible layer, and you have the first RBM, right? So these are all connected, right? So this is RBM 1, right? Then what you do, this hidden layer becomes the visible layer for another set of another RBM. This is RBM 2. Then this hidden layer becomes the visible set of another RBM. This is RBM 3. So this RBM, this is deep because it has so many layers. This is called deep belief network. So deep belief network, why do you need deep belief network? Because what you can do is you can have a belief net, and you can find out relationship between observed and hidden parameters. So remember we discussed that example last class, that there is a differential equation where G, that closed loop blood glucose control, where G, I are observed variables but X is not. X is an unobserved variable, but you still need it to get G and I. You can use a deep belief network to figure out the relationship between G and I and X. Although this is a much smaller scale, so you don't really need a deep belief network. But what if there are large number of hidden variables and large number of observed variables? What do you do then? So deep belief network is just a stacked RBM. Now we come to an autoencoder. Or actually deep autoencoder. So what is a deep autoencoder? It is composed of two deep belief networks. DBN, right? Deep belief network, and the first one is the mirror image of the second one. So that means you have some visible layers, some hidden layers, some more hidden layers, and then you reduce it to these two layers, and then you make it up again. So what happens here is you have the visible layer here, x1, x2, and up to xn, and then you have this autoencoder layer. What are these? These are the same values, x1, x2, xn, same as these ones. So what are you doing here? Giving same values to input as well as output. You are telling the autoencoder, okay, learn the weight so that you can deconstruct the input to some lower dimension, and you make that lower dimension such that using that lower dimension you can reconstruct the input back. Okay? So when you learn the autoencoder, you minimize the distance between these two. Okay? So you can minimize summation x1, and if you say x1 hat, or xi minus xi hat whole square, I equals 1 to n. So you want to make it 0. 0 means, so that means what? You can just deconstruct this, make use of these variables, and reconstruct the output. Now once you have done that, what you do is get rid of this. After training, get rid of this. If you get rid of this, then what it means, the activations of this hidden layer become your low dimensional representation of the signal. So this actually you can use to do PCA. You can get exact PCA results. Exact PCA results you can use in auto. Actually, I won't say exact PCA because there will be some error. So you can imitate principal component analysis. Now we have skipped a lot of things. We have skipped a lot of things. Means okay, we know how to train RBM. We only know how to train RBM with binary values. What if we have real numbers? We have skipped that. Then we have also skipped, okay, we have stacked RBMs, DBM, we know how to train a DBM. We have skipped that. Then we say that, okay, DBM, we make an autoencoder, how to train an autoencoder. We have skipped that as well. Why I have skipped that? Difficult concepts, take a lot of time. And I'm not sure yet whether you want that. And I'm not sure yet whether this class allows me to do all this. Because this is introduction to data mining. So in introduction shouldn't be finale, right? So if it is introduction, we should make it more basic. So I will stop here, but these will pop up. These will pop up as and when we go forward in this course. And my personal aim is to finish up all the things that we'll discuss for exams fast, and then discuss these issues, because I want you to use these in your assignments. So assignment 2 is not uploaded yet, but I will upload it today. I'll upload it today, you'll start. Then from assignment 3 and 4 we can start doing all these. 3, 4, 5. So 3 will be again simple, SVM and all that. 4 will be neural networks. 5 will be these deep things. So let's stop here, and then let's discuss another concept, the concept for clustering, right? Unless you have some questions. Yeah.
What do you mean by PCA imitate? Like, will there be actual error between the actual procedure if I go by?
So it will be error because you are getting this hidden layer based on training data.
So, like if I have 2 nodes in the output, I means that I'm using the 2 principal components.
Yes.
First 2 principal. Even with the traditional way of PCA through eigenvalue or SVD, we get that error in that. So, it will be similar.
No, I mean it will be results different from PCA. It will be another low dimension representation. But if it,
Different from the first principal component.
yes, it won't give you eigenvectors. Any other question?
What's the difference if we use positive consequence and negative consequence in this? Like instead of developing a mirror image of the first half.
No, so in the RDM, you are not exactly reconstructing the data. There is error, and you are firing the hidden layer with a probability, and you don't know whether the output is going to be the same or not, and you don't want it to be the same because you want to give them different recommendations. Those recommendations are from the same probability distribution, but you don't want it to be same. Right? But in this autoencoder, you want it to be same. And you want it to be same so that you can use it as a low dimensional encoding.
Coming back to the PCA imitation point, so when you do PCA, there's a certain amount of loss and variance. So,
No, there is no amount of loss in variance. When you do PCA, there is no amount of loss in variance. You undergo loss in variance when you choose to ignore eigenvectors.
I mean, so basically, when you convert your data into the principal components that you're getting, is that the better representation
Yes,
that you're
definitely.
getting from PCA?
Because if you
or
do
the
not,
one that
if
you're
you
getting from here?
if you do not ignore any eigenvectors, you have all the eigenvectors, then you can get exact data. Now, if you exact reconstruction, if you try ignoring eigenvectors, like ignore the smaller ones, then there will be errors. then there will be errors in reconstruction. But that error is not same as this one, because this one only depends upon what training data input you give me. It is not looking at the entire data. So it will only work for the training data points. Now coming back to his question that, okay, in an autoencoder also, instead of reducing, you can have bigger hidden layers. Right? You can have progressively larger amounts. So that is the thing I am personally interested in. So there is very little work. There is very little work on this. What they are trying to do is they are trying to see whether autoencoders can encode distances. Right? So if autoencoders can encode distances, then that means you can potentially have a solution similar to CNN for time series data. So in that case, they are using autoencoders which have much larger hidden layers than the input layers. So that I don't think we will discuss here. So any other questions? If no questions, let's go to the next chapter. I think it's chapter 6 or something. Clustering. I don't know whether which chapter is this in the book. So you should read the book, because the book has everything that we are discussing in the slides. And then also you should practice questions from the book, because I will choose some of those for exams. Oh no, this is chapter 8. Chapter 8. Okay, so what is cluster analysis? You know, so an example is, let's say I want to curve your grades. So what is curving of grades? So basically, I know what you got in midterm, I know what you got in final, assignments, all those I know. But I don't know what grade you will get. But I have to find it out. Right? So I don't know the levels. I don't know your levels, whether you're an A or a B or a C, I don't know. But I need to find it out. But I know your attributes. Attributes as in the exams, how much you got in your exams. Right? So this is unsupervised learning. So unsupervised learning means I don't have any idea about your labels. I have the training data, but I don't have any idea of labels. Now, this is also discrete unsupervised learning, because I only give you 4 grades, A, B, and C, or D. Okay? I don't give you A minus 0.5, I don't give you that. So that's why this is discrete. So this is discrete unsupervised learning or clustering. So basically this, if I give you this data, how many clusters are there? How many clusters are there?
3.
You say 3. What do you say?
It will depend on the user.
So he says it depends on the user. Any other answers?
3 based on the
3 based on
color.
the color. What else? Anybody says 2 or 1? The answer is pretty vague. And as he said, it's in our mind. We saw, okay, 3 colors, so maybe 3 clusters. But what if somebody is colorblind? A colorblind doesn't mean that he sees the same color. He just doesn't see some colors, right? But if say, let's say a person who sees them as the same, the red is same as pink, is same as green, let's say. So what will that person see? How many how many clusters will that person see? Okay, how many clusters will that person see? If color is not a distinctive factor, then how many clusters? If color is not a distinctive factor, you can still see 3, right? Why? Because there is a marked difference, distance, right? But what if the distance doesn't matter? You can see 1. So these clusters are in our mind. These clusters are in our mind. So how do we tell to a computer what is in our mind? And how do we see that a computer is exactly representing what is in our mind or not? It's difficult because we don't have the ground truth. We don't know what is in our mind. Maybe by looking at the data, it seems like since they are spread out in space and they have 3 different colors, there might be 3 clusters. But does it make sense, 3 clusters? Do we really have 3 clusters? So the ground truth here is shaky. When the ground truth is shaky, how do you train a machine or how do you make a algorithm that gives you correct results? Because you don't know what is the correct result. So clustering is more difficult than what it sounds. So it is difficult. So now one way to encode what is in our mind. One way to encode what is in our mind is to follow this way that the book says. So there are 2 distances, intra-cluster and inter-cluster distance. Right? So what is intra-cluster? So intra-cluster distance means 2 points in the same cluster. The distance between 2 points in the same cluster. And there is intra. And inter-cluster means distance between 2 clusters. Right? So one way to encode what is in our mind is the clusters are such, you group the data points in such a way that the intra-cluster distance is minimized and the inter-cluster distance is maximized. Right? If you see that, the average intra-cluster distances are minimized if you have those 3 clusters, and the inter-cluster distance is maximized. Right? So that kind of encodes what we think. But is that the correct one? We don't know. Nobody knows. So it shows application of clustering. There are many different applications of clustering. You don't have to restrict to all these. It can be geographical clustering, it can be population-based clustering, density-based, so many different types. We'll see examples of these. Don't have to read what is not clustering. Okay, so whatever question we are discussing or trying to answer, they are asking the same question. So if you are given this data point, how many clusters? There are multiple answers. So maybe there are 2 clusters, or maybe there are 6 clusters, or maybe there are 4 clusters. Which one is correct? Okay. So one way to do it is that minimize the intra-cluster distances, maximize the inter-cluster distances. So often I confuse the 2 because you have to tell me whether I'm confusing or not. Inter and intra. I always have to stop and think. So there are many different types of clustering. So there are 2 types. hierarchical and partitional clusters. So partitional clusters means each cluster they are mutually exclusive. So if you have two clusters in a data point, there are no points that belong to the same cluster, that belong to two different clusters. And each point belongs to at least and at most one cluster. So that is partitional cluster. And hierarchical cluster means one point can belong to multiple clusters. It can belong to multiple clusters. So we'll see examples of this. So partitional cluster is like this, and hierarchical cluster is like that. So it's the same data point, right? P1, P2, P3. No, it's not the same. So just one data point is missing. Okay. So now to represent hierarchical clustering, or to represent the way you make a hierarchical cluster, you call it a dendrogram. Right? What is a dendrogram? So what you do is, using a dendrogram, you can say how the cluster was made. So if you look at this, P1 is connected to a cluster, so don't look at that. P4 is connected to another cluster, don't look at that. P2 and P3 are connected together, so this is the first point. So which means that P2 and P3 was grouped together first. Right? Then that group was connected to P4. So P2, P3, P4. And then that group was connected to P1. So using a dendrogram, you know how the cluster was created. So now if you see that P3 belongs to this cluster, the smallest one, the medium one, as well as the larger one. So P3 belongs to 3 clusters. So these clusters are not mutually exclusive. So that's why these are not partitional. Right. Now there are many other different types of clusters. So exclusive versus non-exclusive. So in non-exclusive clusters, point may belong to multiple clusters. Okay? So it's just not hierarchical. You might have intersection between clusters. It's not hierarchical cluster, but here points are belonging to multiple clusters. So that is non-exclusive. Fuzzy versus non-fuzzy. So fuzzy versus non-fuzzy means you are saying that, it sounds that it might not be that useful, but it is kind of useful. So fuzzy clustering means you are saying that one point may or may not belong to a cluster, right? So with a certain probability. So, so you say that one particular point can belong to any cluster, all the clusters. If there are 3 clusters, this point belongs to all 3 clusters. But the probability that this point belongs to cluster number 2 is 90%. The probability that this point belongs to cluster number 1 is 20%. And that this point belongs to 3 is 5%. So you can say that. So that is fuzzy versus non-fuzzy. Partial versus complete. So complete cluster means all the data points belong to some cluster. And for each data point you will have some cluster. And partial means there might be some data points that do not have a cluster. Typically when you have outliers. And when you say that, okay, this data point doesn't make sense, this outlier. Right? But that is a dangerous thing to do in research. When data don't make sense, it's not an outlier. It might be something important. Right? So, but often we make some assumptions because our model doesn't fit. So we just say it's an outlier. Then heterogeneous and homogeneous, these are not that important, but this is just cluster of widely different sizes, shapes and densities. So there are different types of clustering. So we can call them well separated cluster, and so these are different definitions of clusters. So if you go to the cluster level, there might be different types of clusters. So well separated clusters, center based cluster, contiguous density, all that. So let's go one by one. So this is a well separated cluster. What does that mean? So a cluster is a set of points such that any point in a cluster is closer to every other point in the cluster than to any point not in the cluster. So this is the same concept of minimizing the intra-cluster distance and maximizing the inter-cluster distance. Right? That if you do that, you get a well-separated cluster. Now, center-based cluster means all points are closer to the center. Right? So a cluster is a set of, this type of cluster is a set of objects such that an object in a cluster is closer to the center of the cluster than to any other center. So that is center-based cluster. Now you can also call it centroid, or if it is an average of all the points, then you call it medroid if it is the most common value. Right? Contiguous clusters, these are interesting. So contiguous cluster means, so now this definition is kind of hard to grasp. So what is it saying? That is saying that a cluster is a set of points such that a point in a cluster is closer to one or more other points in the cluster than to any other not in the cluster. That is the first one, and that is distance based. Now two objects are connected only if they are within a specified distance of each other. So that's where you get the contiguous part. So what they are saying is that, okay, you specify a distance, can be Euclidean distance, Manhattan distance, whatever distance, and you give me a threshold. So a distance and a threshold. So what is a cluster now? If two data points following that same distance metric, if two data points have a distance less than the threshold, I will call them that these belong to the same cluster. So in that case, what you will have, you will never have holes in your cluster. You will have a contiguous set. So that is contiguity based cluster. So if you consider this figure, this is a contiguous cluster 1, but this is also a contiguous cluster, right? I mean, there are two contiguous things and these are connected by a string of points. So this becomes one cluster, this whole thing, is a dumbbell shaped cluster. Right? Now the problem is those points might be outliers, those points might be noise. You actually have two clusters, but those points are connected by noise. You want to eliminate that. So these contiguity-based clusters are not good for that, because if there is noise, then it gets easily affected by them. Right? So there are different advantages and disadvantages of clusters that we'll talk about in a bit, maybe next class. Then there is density-based cluster. So density-based cluster means density of points, right? So if you see here, if these two were connected by dots, if these two were connected, these are not, but if these two were connected by dots, then they will be classified as multiple different clusters because the density is ever changing. So whenever there is, so what you do here, a density-based cluster is that you have a density metric. What is density metric? Number of points in a unit area. You can use that, or you can use some other metric. So you have a density metric, and you set a threshold and say that, okay, if density changes by this much, then I will say that this is a separate cluster. So this is density change, not on the density, the change of density. So if density changes a lot when I move, then I will consider it as a different cluster. So in this case, there will be 3 clusters on the right hand side, right? And there will, on the right, no, left. Yeah, on the left hand side we will have 3 clusters. The middle one only has 1 cluster. Density doesn't really change. And again, this one has 2 clusters. Let's discuss this later. We'll now go into clustering algorithms. So let's discuss this next class. No, time is because we're 28. No. The exam is on 28th, right? It's not on 21st. 28th. So somebody heard that it is on 21st. Gave me a shock. Just stop it and take it. Yeah, I will.